Okay, so we are starting today section 1.6, which is all about information theory. Now, information theory is a really big topic. It's a really deep topic, really worth learning more about if you have the time and the interest. And there are lots of great books out there. Some of them are actually listed here. The Cover and Thomas is the classic. Mackay also has a really great and really fun book on information theory and other related topics. So really worth knowing a lot about. This particular section is just going to cover the chunks of it that we're going to be using later in the book. So we're not going to touch on everything, but we're going to talk about some of the really important concepts that we'll use, in pattern recognition and machine learning, etc. As they come up. So definitely, if you don't know much about it, I would highly recommend looking into it. It's really cool and really it gives you a new perspective on a lot of the questions that come up in machine learning, in pattern recognition, in neuroscience, which is what I work on. So really worth the time you put into it. So let's get started. So the very first thing we need to discuss is that when we're talking about information, we don't mean semantic information. So we're not talking about meaning. The game is always going to be about you want to send some symbols down a channel. So sorry, I'm using some terminology. You just want to send some symbols to a receiver. So you're a sender and you want to send to a receiver. And the kinds of questions that come up is, if how much can you compress the symbols that you want to send to kind of send the stream of symbols more efficiently? Or if there's some noise in the process, can you encode your symbols in such a way that the receiver can decode them perfectly, despite the noise in the process, and with the conditions under which that's possible or that it's not possible. And so there's no notion of what the symbols actually mean. It's just, you have A, B, C, and D. Does the A, B, C, and D get across to the other side, regardless of the fact that A for you might actually mean something important, like, I don't know, who won the World Cup or something like that. So it's just about the symbols themselves. And actually, so the original paper that kicked off this whole field was called A Mathematical Theory of Communication. Definitely worth looking at. And again, at the very beginning of that, it's really hammered home that it's all about sending, where we just care about symbols, sending symbols down a telegraph line, a telephone line, and we don't care at all about what the symbols actually mean. So the interpretation of those symbols is up to us as humans. We just care, can I get the symbols from this end to that end, and without errors, and as efficiently as possible. So that's what we're talking about. The next thing, so that then motivates. So now that we've got these symbols that we want to send, the next key piece is, of course, that there's going to be some uncertainty in the symbols that we're going to send, right? So if the receiver always knew that we're going to send the sequence ABC, well, there's no point in having a communication there, right? Like you could just assume it's been sent. So there's a notion of randomness that has to be involved. Otherwise, the communication doesn't really make sense. So why communicate if your receiver already knows what you're going to send? So we're going to be talking about random variables. That's going to be important. And for at least this first section and the initial development, if you look at the original paper as well, we're going to be talking about discrete random variables. So random variables that have a discrete number of states. So for example, like letters in an alphabet, Morse code, 0, 1 bits, in digital communication, we use that all the time. So that's the domain that we're going to be working with. So we have discrete random variables. And now we have to talk about, okay, so so the question we're asking is, how much information is received when we observe a specific value for this variable? So the question is, what does that even mean? Like, what does it mean that we received information? And how do we measure that? So in this kind of first paragraph, we're going to talk about how to come up with a reasonable definition of information that agrees with our intuitive notions. And so the way we're going to approach it is that the amount of information can be viewed as a degree of surprise on learning the value of x. Okay, and there's actually a kind of a very recent example of this. So I think it was about last week or something. There was news that in Dubai, so in the Middle East, very on the Arabian Peninsula where it's very hot, very doesn't rain very much. There was all of a sudden there was floods. So it rained so much there was just mass flooding, and people were unfortunately stranded in the airport, etc. So now imagine that you are, let's say you are a person, and you are a person in Dubai, and you're communicating with your friend, let's say in the UK, and the only communication you have is you send him symbols. One symbol saying, it's sunny in Dubai, and the other symbol is it's been raining, heavy rain in Dubai. So you have just two symbols, A and B. Now, most of the time, your friend, every day you send them what's happening. Most of the time, your friend is just going to receive the symbol that it's very sunny in Dubai. And he's not going to be surprised. At some point, he might even stop checking those messages because he just gets them all the time. But then all of a sudden, one day he'll get a message saying, the message B, heavy rain in Dubai. And intuitively for us, that's going to be a very surprising event. If that message was, meant flooding in Dubai, that would be a very surprising event. Now, importantly, though, notice that, right now I'm attaching meanings. Well, A means sunny in Dubai. B means, let's say, there's been a flood in Dubai. So, but in this context, all that matters is that this message, sunny in Dubai, has a very high probability. So the symbol A comes across every day, maybe like 0.999. And the symbol B maybe has a 0.001 probability. And it seems that when our friend receives that message, regardless of what it actually means, that's kind of a very informative thing. Something that very rare has occurred. Effectively, that's what we're saying. So he'll be very surprised to have received that message. And so it kind of makes sense that actually, information in this context of when we're just dealing with symbols should be related to the notion of surprise. So how surprised are we to receive have received a particular message out of the set of possible messages? And he kind of talks about that here. So he says, for example, if we're told that a highly improbable event has just occurred, so just like the flooding in Dubai, we will have received more information than if we're told that some very likely event has just occurred. So a sunny day in Dubai. And if we knew that the event was certain to happen, we would receive no information, right? So that kind of goes back to our original case of like, if you're just constantly sending the same message, then there's no information. The downstream person just knows you're going to send that all the time. Why even communicate? So he says, our measure of information content will therefore depend on the probability distribution P of x. So again, in our example of the weather in Dubai, there's going to be two messages. It's raining, it's sunny, or there's a flood. And those messages have different probabilities. And the degree of surprise for us as a receiver is going to depend on the probability of the message we received. So, we're still, okay, we're just kind of still playing qualitatively with, these notions of information. So we said we therefore look for a quantity h of x that is a monotonic function of the probability P of x. So monotonic just means it's either, it goes up as P of x goes up, or it goes down as P of x goes up. So it doesn't go, this quantity shouldn't, for some, it shouldn't increase at first and then go back down as something gets more probable. It should either, whenever the event gets more probable, either our quantity should increase or it should decrease. So that's monotonic. So it has one tone, I guess. So either going down or going up. And it sounds like, based on our discussion, we actually want our notion of surprise to increase with lower probability. So as the probability increases, we want our information to actually come down. So as the sun in Dubai is much more probable than flooding in Dubai, and we want the sun in Dubai message to be less surprising, to have less information. Okay, so that's so we've got the monotonic piece out of the way. And now it says, okay, the form of H can be found by noting that if we have two events X and Y that are unrelated, then the information gained from observing both of them should be the sum of the information gained from each of them separately. So that's just saying that, let's say we've got our our weather in Dubai case, and something else, maybe like who won the ice hockey championship. So those things are generally going to be unrelated. And so we want, if someone tells you what the weather in Dubai is, and your other friend tells you who won the ice hockey championship, the amount of surprise you should have from those two independent events, those two unrelated events, should be the sum of the surprise from each of them individually. So that's kind of an assumption, but it seems like a reasonable assumption that your surprise from unrelated events should sum. That's what we're talking about here. So the sum of information gained from each of them. This is your surprise of getting x and y should be the sum of h of x plus h of y. Now then we combine that with the probabilities of those events. So it says two unrelated events will be statistically independent. So that's kind of what we mean by unrelated. And so the probabilities will be the joint probability will be the product of the marginal probabilities. So from these two relationships, it's easily shown that this information measure we're looking for receiving x must be given by the logarithm of p of x, right? So the logarithm behaves just like that, right? So the log of p of xy, if they're independent, if they have this form, is going to be the log of p of x plus the log of p of y, and that looks a lot like what we need. So you can show that from this and maybe a couple of other basic assumptions that the logarithm is this is the function you're looking for, this monotonic function of p of x that behaves in this additive way for events whose probabilities are independent. So let's scroll up and see what we mean. So here we have it here. So we've got h of x. There are the information that we receive about having about our notion of information when we receive x is minus the log of p of x. So that's what I mentioned before, that we want events that are getting more probable to become less informative. That's where the minus sign comes from. Another way of writing this, if you want to avoid the minus sign, you can just write this as log of 1 over p of x. Right? So as p of x tends to 0, this becomes much more informative. So yeah, so that's kind of our what we're going to be using as information about a particular symbol. One minor point here is that we're using base 2 logarithms. So there's always a question of what logarithm to use. Ultimately the base doesn't matter. It'll just add a multiplicative term here. But in different contexts, certain bases are kind of more natural. So digital communication, log 2, so bits are going to be really much more natural to use. In other contexts, you might use the natural logarithm. So that's just a convention. You could use whatever you want. The key thing is this logarithmic relationship. Okay, so that's kind of that's how our notion of information and how that connects to the probability of an event. So now let's build up to kind of we're very close to the key concept in information theory. So now suppose that a sender wishes to transmit the value of a random variable to a receiver. So now we're not talking about just one message. We're talking about sending all possible messages, but corresponding to their probabilities. So the average amount of information that they transmit in the process is obtained by taking the expectation of 1.92, so this thing, which was for just one symbol, with respect to the distribution p of x. So here we've got our log 2 of p of x, and the minus sign is there, and now we're going to take the average value of that. So now we're summing over all of the x's. So how much information am I how much the average amount of information I'm going to send to my friend about the weather? Well, it's going to be the probability of of sun in Dubai times the negative of log 2 of that probability, plus the probability of there being a flood in Dubai times the negative log 2 of that. So the average amount of information we send, and this important quantity is called the entropy. So entropy is very important. This is going to be the thing that if you haven't seen it, this is the central quantity of information theory. It's called the entropy. So this is your average surprise about receiving or sending or receiving messages from a given probability distribution. So notice it's one thing to point out. It's here we've got h of x, but notice that this is actually a function. It's a bit of a weird way of writing this, because you'll see that the x is actually getting summed over. So h is actually a function of p, which is a function of x. So it really, but people write it in different ways. So you have to just be careful that. So this should actually be h of p, and p is it's probability distribution on x. So entropy is actually it's a function of a probability distribution, a probability mass function in this case, because we're talking about discrete states, discrete symbols. but when we talk later, we'll talk about continuous probability distributions, and there it'll be what's called kind of a functional. So it's kind of a mapping that takes a function, in this case a probability, and gives you a number out. So just be careful with this particular notation, because yeah, it can be a bit confusing. Just remember that H is always it's a function of a probability distribution. So it doesn't really make sense to say what is the entropy of a single symbol. What's the entropy of it being raining, it being sunny in Dubai? That doesn't make sense. We can talk about the information of it being being sunny in Dubai, but the entropy is, you have to talk about the whole set of possible, let's say, weather conditions in Dubai, and you can talk about the entropy in that. So just be careful about these notational issues. Yeah, and just a minor point to know that the limit as p goes to 0 of p ln p is 0, and so we're just going to have this convention that p of x ln p of x is 0 whenever p of x is 0. So it just means that the entropy contribution of events that never occur are going to be 0. So we don't want, ln of p of x is going to minus infinity, so you just have to take the limit and use the convention that we're going to use. So the p of x equals 0 case aren't going to give us a problem. Oh yeah, and one other point I wanted to mention is, so it's natural for us to think that information should be a 0 or a positive quantity. So just notice that we get that for free here, because p of x is only going to ever be less than or equal to 1. So 1 over p of x is going to be greater than or equal to 1, so this means this will always be positive, 0 or greater than 0. Okay, so I think that was the definition of entropy, really important topic. Now let's kind of look at it from a slightly different perspective, but an equally important, equally powerful one. Okay, so it says, we now show that these definitions indeed possess useful properties, and they possess, they're really, I think, really kind of profound and really interesting concepts. And we're going to look at it first in this section from the perspective of sending messages. In the next section, we're going to actually talk about the original notion of entropy, which came actually from statistical physics, and that'll also give you a different perspective on the concept. Okay, so consider a random variable x having 8 possible states, each of which is equally likely. So that's the important bit. So imagine that just the letters, A to H, but they're all equally likely. So unlike in English, where A will be much more likely than H, I believe, and E certainly will be more likely than H. In this case, we're going to assume that these letters are equally likely. So let's just compute the entropy for that distribution. So what's that going to be? So we're going to have, let me point out. So this is going to be P of x. These two, I guess together with that's going to be the minus log P of x. And then there's 8 of these. This is kind of the sum on x. They're all the same. So that's where the 3 bits comes from. So we're just doing this simple calculation here, but our P of x's are all equal to 1 over 8. So it reduces to this simple case. Maybe I'll just write that. So P of x equals 1 over 8 for all x. And that's what this equally likely means. We have 8 items, they all have the same probability. So in that case, we found, okay, it's got 3 bits. And that, if you know anything about, digital communication, kind of computers, you're like, yeah, that makes sense. I have 8 variables, and I want to assign them to, assign them to binary digits. Well, how would you do that? And you would say, okay, well, I'm going to have, 0, 0, 0, 0, 1. Maybe this could be A, this could be B, 0, 1, 0, etc. All the way to, 1, 1, 1 for H. So yeah, you're like 3 bits. Yeah, of course. Like that kind of makes sense. That has a nice, congruence, or, I don't know. It kind of agrees with what we think from computers and what we know from that area. But now let's look at an example where, so again, we have the same 8 symbols, 8 states, for which the respective probabilities are given by this. So notice that now A is going to be very probable. And then these last 4 are actually going to be quite rare. So E, F, G, and H are going to be quite rare, and then the others are somewhere in between. So now if we compute the entropy for this distribution where the one of the symbols is very, very frequent, and many of them are actually quite infrequent, but still 8 symbols, we see that the entropy now is 2 bits. So this 2 bits is less than 3 bits. So somehow there's, when we're dealing, if we're talking about the information content, the entropy of this distribution is actually less than the one where everything was uniform. And that, that should kind of make some intuitive sense, because, in the case of when everything is uniform, you basically have no idea what you're going to receive from one message to the next. All of them are equally likely. But in this for this particular distribution, we're pretty sure half the time we're going to get A's. A good chunk of the rest of the time we're going to get B's and C's, and then sometimes we'll get E, F, and G, and H. So somehow we actually have, it kind of makes sense that maybe this distribution has lower entropy. There's less uncertainty about what we're going to receive. And that's what we talk about here. So we see that the non-uniform distribution has a smaller entropy than the uniform one. And so he says we're gonna get some insight into this in the next section when we talk about entropy and disorder. But let's just talk about how we would kind of send these messages along the line. So it says we could do this as before using a 3-bit number. So that's what we talked about up here. We could just assign them just as as in exactly the same way. But it turns out, and this is the key bit, and this is kind of like the crucial. This is just like a tip of the iceberg of a huge part of information theory, which is all about data compression. How much can you compress data when you know what the probability distribution of the symbols is, and then how do you coming up with those compression algorithms? Okay, so we can take advantage of the non-uniform distribution by using shorter codes for the more probable events, but at the expense of longer codes for the less probable events. So okay, so what does that mean? And it says in the hope of getting a shorter average code length. This can be done by representing the states A, B, C, D, E, F, G, and H using, for instance, the following set of code strings. So it says, well, remember that A was the most probable, so we're going to give the shortest, the shortest code. There's 0 and 1, so we'll pick one of them. We'll say we'll make it be 0, and then we'll give B 1 0. We'll give let's say C 1 1 0 all the way to, and then these really rare ones are going to get very long strings. So actually longer than we had before, right? So before, our largest all of our strings that we were using had 3 bits. So it was 0 0 0 0 all the way to 1 1 1. Here we actually are going to have some messages that have 1 bit, but some that we assign actually kind of these 6-bit strings to. So at first it might seem, well, that might, how is that going to make our code shorter? But it turns out that it does, because we've assigned the shorter ones to the more frequent messages. So it's almost like, you can actually almost think of this as like, don't send anything if A occurs, because we just know that's what's gonna, A is gonna be the default. If I don't get anything, I'm gonna assume A happened. So it's only when I get other messages that I'll know that, okay, A didn't happen, something else happened. So the average length of the code that has to be transmitted is then, and we just compute it as before. So we half the time. So let's just do this. So this is going to correspond to A. So half the time we get A, and its length is 1. Then a quarter of the time this is B. This is C. I guess this is D, and then these 4 are E, F, G, and H. And notice that now this is actually, we've managed to on average send a much shorter sequence. So instead of sending, 3 bits all the time, we're now going to send, we only need 2 bits. So we send about 2 bits of information, 2 bits of 2-bit strings basically. And because of the clever way that we've actually assigned code words, which again is the same, which again is the same as the entropy of the random variable. So it's kind of like, oh, it says 2 bits, and we actually found out the entropy was 2 bits. Like, is this a coincidence? Can we do even better? And we'll talk about this point in a second. But yeah, this relation between entropy and shortest coding length is indeed a general one. So that means that there's this famous theorem, the Noiseless coding theorem, which is kind of what's important for compression. So there's no noise in the process, but how much can I squeeze? How efficiently can I transmit a set of symbols coming from a probability distribution? It says that the entropy is a lower bound on the number of bits needed to transmit the state of a random variable. So it says that we can't actually do, on average, as the number of states that we want to send. So let's say we've got these 8 messages, but we keep observing them, and we want to kind of send that that long string of that state sequence. The entropy is a lower bound on the number of bits needed. So on average, we can't do better than the entropy. We can't find a more efficient code than that. But if we find that our code is maybe it's taking 2.5 bits, then the theory says that, hey, you're not quite at the lower bound yet. So there might be a way to actually compress. Maybe there's a more clever way of compressing your messages, of assigning them to source coding. So kind of assigning these symbols to strings that will allow you to send your messages more efficiently. So you can't do better than the entropy. The entropy is a lower bound. And if you're doing worse, it might be possible to actually improve your code. So the last point I just wanted to touch on was this one here. So that the shorter code cannot be used because it must be possible to disambiguate a concatenation of such strings into its component parts. So yeah, and he kind of gives the example of this 11001110. So he says, okay, well, this decodes. We can just look at that and just chunk it up and decode C, A, and D from it. So let's just do that. So 1110, so that's C, and then so we just look at that. We're like, yep, that's a code word. Now then we look for 010. We know is a code word, so that's going to be A. That's going to be A, and then 110. That looks like that's going to be D. Right, so we just take the strings and we assign them one-to-one to our states as the strings come in. We just process them and assign them. So now, for example, imagine you're like, well, maybe I can get a more efficient code if I replace this 10. Maybe I could assign 10 to state C and give B the code 1. Right, so imagine a code where we had A is equal to 0, B equals 1, C equals 1 0. Well, all of a sudden you can see there's going to be ambiguity, right? Because if you get, let's say your friend sends you the message C 1 0, well, you can't tell whether that's what they meant or they meant A followed by B. So that's what he means, that it must be possible to disambiguate a concatenation of such strings. So you need to be able to map kind of one-to-one from the strings that you receive to the sequence of states. And if you have a code that can do that, then this noiseless coding theorem says that on average, the average amount of bits that you need to transmit that message is lower bounded by the entropy. So the entropy is it's not just our average surprise. So it's got that interpretation, and we'll see it's got that interpretation in terms of disorder, but it also has interpretation in terms of how much you can compress the states, the information you're sending, based on the probability of the different states. So I think this should give you some of the taste for what an interesting and deep topic information theory is. Okay, so I think I'm going to stop there for now, and then we'll just continue. It's a bit of a long chapter, so I think I'm going to break it up, and we'll just continue from where I've stopped here, where we'll talk about a more physics, the motivation of entropy from physics, where the notion first emerged, and that'll give us even more insight into the concept. Okay, so thanks for hanging out, and I'll see you next time.